Okay, so question 1A, an absolute gift for 6 marks, that was what we want. A flagpole is held vertically by 2 wire stays attached to the same point on the pole. That's good. The 2 stays are at angles of 40 and 30 to the pole. Complete the vector diagram and calculate the resultant force R. So literally all they want us to do is resolve these into the y direction. Okay, seems a little simple, but let's go for it. So complete the vector diagram. So I'm guessing by that what they want us to do is to show that there will be y components and x components. So we can say R is equal to, if we call this T1 and T2, we can say T1 plus T2. And then we can say that there's also an x component. Oops, that's going to be vertical, horizontal. We've got an x component here. Right, so let's resolve away. Okay, so T1 cos 30. So R is equal to T1 cos 30 plus T2 cos 40, which is equal to 1400 cos 30 plus 1100 cos 40. Slap that into the calculator. And that comes out as 2055.08 newtons, which is equal to 2.055 kilonewtons, which is to one decimal place 2.1 kilonewtons. Right, let's check our answer, which you don't have the benefit of doing in the exam, but answer 1, 2.1 kilonewtons. 6 marks, thank you very much. 6 marks in 2 minutes 30, we'll have that. Right, on to 1B. Question 1B, a steel rod of length 0.8 metres, diameter 25 mil, 4.2 of its length, 50 for the rest. What will be the extension in the rod when it's subject to an axial, meaning along the axis, the length of it, of 10 kilonewtons? Right then, I'll follow my own advice. I'm going to draw a diagram. Nice. Mine isn't going to be particularly neat, given I'm using a graphics tablet, but I'll do my best. Okay, so I've got still 25 and 50 for the rest, so it roughly doubles in size. And I'm not entirely sure where I'm going with this yet. I'm trying to do this as honestly as possible and not prepare the answers first. So I'm just following my own advice of draw a diagram, write variables. Right, a steel rod of length 0.8 overall. There we go, didn't know I could do faint lines, that's good. Right, still at 0.8. A diameter of 25 mil, so diameter there of 25 mil. So that's 0.025. And you're going to be quicker in real pen rather than my graphics tablet effort here. For 0.2 meters. Okay, this is starting to feel like an extension question across 2 separate lengths. So, and for the rest of it, it'll be 50 mil. So that's diameter 2 of 50 mil, which is 0.05 meters. And so that's going to be 0.6 logically, isn't it? What will be the extension of the rod when it's subject to an axial force of 10 kilonewtons. 10,000. I like to get into the habit of writing it down longhand straight away so you don't make any mistakes. Young's modulus, which we know is E, is equal to 200 gigapascals, so 200 times 10 to the 9. If you just write 200, you will make a mistake and just calculate with 200. So it's gigapascals, 10 times 10 to the 9. Right then, I've got a good idea what's needed here because I see an E. So let's have a look at our formula sheet though. I'm sure I downloaded a formula sheet. There we go. Right, let's have a quick look. And this is the one that I recommend you take with you in the exam. We've got some stress analysis-y type stuff here. Here we go, stress and strain. This is the basics. So we've got stress is force over area, strain, epsilon is delta L over L, change in length over length, and Young's modulus is stress over strain. Let's stick all those down and see where it gets us. So, state formula, draw diagram, state formula. So we've got Young's modulus, E, is equal to stress over strain, where stress is equal to force over area. Area, we've been given diameters, you know where we're going there. Strain is equal to change in length over its original length. What will be the extension of the rod overall? So we're going to split this into two different cases. So we'll call this section here case A, and this section here case B. So then we'll go for case A. Tell you what we'll do actually, we'll calculate the areas first. So the area of section A is going to be equal to pi r squared. So r is, so it's 0.025 over 2 squared. Area of B, the bigger section, is going to be pi r squared, which is 0.05 over 2 squared, which will be equal to, I'll plug those into the calculator. There we have it, two values of A and B. Right then, if I can work out the stress then, that's all I can do at the moment, isn't it? Because I don't have the extension or anything like that, so let's deal with the stress. So we will take the stress in A and the stress in B. Stress in A, force over area. Well, the force is the same in both, which is 10,000, isn't it? Yeah, 10 kilonewtons. So we've got 10,000 divided by the area. So the area of A was 0.00049. And the area B was 0.0096, I think. Just check my calculator. Yeah, 0.00196. So that gives me stresses of those two there. And just looking at that, the stress in the thicker section is less than the stress in the smaller section, which we'd expect, wouldn't we? So what else can I do now? I've dealt with all the stresses. Can't work out that yet. I know my original length, but I still don't know my extension. That's what we want. And yeah, I can't work with that yet. So I've got to work out this. So it looks like if I can work out my epsilon and my strain in both sections, and I can go ahead and calculate that. So let's deal with this next. E. So we'll state our formula. E is equal to stress over strain. So stress A over strain, which is what we're trying to find out. So we can rearrange that to be, in fact, I'll just get rid of that, doing generic terms to begin with. So I can rearrange this to be strain is equal to stress divided by big E. Yep, checks out. Yep, so then I can go and plug this in here. Right, so strain at A, strain at B. So we've got stress of A, so that's going to be this thing. I'm cheap, why not? Both divided by 200 gigapascals, so 200 times 10 to the 9. That's going to equal. There we go, calculated two strain values which are unitless nature. Strain is roughly just amount that it's extended, isn't it? So it looks like this has extended less than A, which makes sense because it was thicker, so it was going to stretch less. Right, the only last thing that I've got to do now is work out the delta L for each one, sum them together. So I'm going to just stick in if epsilon strain, which I've worked out here, is equal to delta L over L, then delta L is equal to strain times the original length. The original length is going to be of each section, so 0.2 and 0.6 respectively. So I might just make this a little smaller here. It's not letting me do that. Will it let me do that? Yes, it will. That'll give me a bit of extra moving time. Okay. Right. So let's go. So delta L for section A is going to be equal to the strain there, so 0.0000102 times the original length of that section, which is 0.2, which is equal to something. Delta L for section B is going to be strain times L, so 0.0000255 times 0.6, which is equal to, right, I'll stick that in the calculator. There we go, so I've worked that out. So the total change in length will equal change in length A plus change in length B. And when I stick that in the calculator, I get 0.1234357 meters. Times it by 1,000 to get it in mil. That would be fine to leave the answer as that, but let's times that by 1,000. So we get 0.0357 millimeters extension across the whole bar. Let's have a look. 0.0357 millimeters. Boom. That's 8 marks. Excellent. Let's move on to, is it the third part of the question? Is there part C? It's nice to be able to check the answers, isn't it? Yeah, there is a part C. Calculate maximum bending stress. So it's something that involves bending stress and eyes. Pays to have a quick flick at the old formula sheet. It's this formula here, isn't it? Bending stress, you've got I, distance from centre. It doesn't give us a Young's modulus. So it'll be this half, I should think. Right then. I'm just going to clear some space on my palette here. Right then. I couldn't actually work out how to extend my canvas, so I've got it on 2 separate documents now. Okay. So we've got a cantilever beam supporting 2 loads, has an I cross section. Calculate the maximum bending stress. Let's have a look at our formula sheet then. And we've got mi over sigma y. Let's remind myself, I'll make a mistake at this stage. M over I equals sigma over y. Right, so y is distance from neutral axis. That's an easy one. So this whole thing appears to be 160 mil long, therefore y is equal to 80 mil. That's useful. Bending stress is the thing that I want, isn't it? Calculate the maximum bending stress. Okay, so sigma equals dunno. N. The maximum bending moment. Okay, don't know that yet either. And I is simple enough to work out. So I will be, well, from memory it's BD cubed over 12 minus little BD cubed over 12. We'll just check that on the old formula sheet. Assuming they give it us, of course. I'm sure they do. Oh, they don't. Solid rectangular bar. So you've got your notes, but essentially all it is the big BD cubed is here, and then you make a little rectangle out of these two, and that becomes your other BD cubed. So your little d would be 100, and your little b would be 80. Okay, so we can go from there. Right, I'm going to start calculating that. So I'll just define B, big B, where big B, big breadth, is going to be 40, add 70, add 40. No, I won't embarrass myself in an exam situation. Use the calculator instead of the mental arithmetic. That's 150. Big D, we've already worked out, is 160. Little b, we said, was 40, at 40, which is 80. And little d is, little depth is 100. So I can say I is equal to 150 times 160 cubed. That's important so you realise it's the 160 that's cubed, not 150 times 160 cubed. just the 160 that's cubed. And I realise I'm doing it not in SI units. Okay, let's try that again. So 150 millimeters is going to become 0.15. 160 is going to become 0.16. 80 is going to become 0.08, and 100 is going to become 0.1. Something to watch out for there. So try again. BD cubed. In fact, I'll give myself a bit of room here. So I is equal to 0.15 times 0.16 cubed over 12 minus little b 0.08 times little d 0.1 cubed divided by 12. Try and stick that in your calculator all in one. Plenty of brackets. I would bracket the top, bracket the bottom, and I'd bracket that whole thing there as well. So it looks something like that when you put it in your calculator. Let it do the work for you. I'll do that now. So the I for this given section is this value here. Now normally what I would have done is I pressed the ENG button on my Casio calculator, written it in standard form, but seeing as I've left it at work and I'm working on my phone, I'm just going to write it down like that just to make sure it's right. Now the only thing we're missing out of the equation, let's have a look what we've got so far. We've got that 80 mil. Let's just change that into sensible units. So that'd be 0.08 meters. We're missing the maximum bending moment. Now, I suppose this is a bit cruel, because what we're going to end up having to do is working that out from the cantilever diagram. So we're going to have to make a shorter version of the beam bending question, which is a shame because we like those questions to come up on their own. So I'm just going to draw some lines down here. And if you think about what a moment is, it's force times distance. So if I just slap an axis through here, I work back from the wall. Right, distance from the pivot is 0, so bending moment is 0. I've got 2,000 times 200. So that's going to be 4,000 Newton meters. Oops. Oh, don't know how to draw a straight line. Okay, that'll have to do. 4,000 Newton meters. And then we've got 3,000 times 4, which takes us to 12,000. 12,000, that's going to take us to 16,000. I really don't know how to use this bit here. So it's a 3 times 4 to give us 12,000, add on the 4,000 there. Then we've got 0 force times 5. That takes us back to here. So we've got a maximum bending moment of 16,000. Okay, so we can say that our M is 16,000 Okay, so let's plug it in and see what we've got. So we're just going to have stress is equal to my over I, which is from here. Now I think bizarrely they give you that on the formula sheet despite... Oh no, they don't. They give it on our formula sheet. They don't give it on the official one. Quite rightly expect the people to be able to rearrange this. Okay, so let's stick some numbers in. We're going to have 16,000 times 0.08 over I, which is this crazy value here. You know what, I'm going to copy that. Let's see what that equals. That equals, I get that to be 28,764,044.94 is stress, so it'll be pascals. And then probably one sensible unit, so 1, 2, 3, 4, 5, 6. So that's going to be, you just press the eng button. I forgot my calculator. So 28.764 megapascals. That's what I reckon it is. Hold the breath. 28.74, so there'll be a rounding error. That will be fine. Okay, so that was actually quite a difficult 6 marks. It's a lot to do for that 6 marks, but we got it anyway. I think the bit that we need to just take a note of the time, so that's 27 minutes for 20 marks, which is, by my reckoning, roughly 0.75 marks per minute. There's 100 marks available. This is going to take us 75 minutes to complete the paper at this rate then. 75 minutes. Oh, we're going to be done in half the time at this rate. Anyway, that's an aside. We're well on track with time. This, I just want to spend a little bit of time explaining, because this is something we haven't really seen. Okay, I'm going to take an aside. I'm going to just do a beam bending question, a simply supported beam, just to show a principle. Right, okay, so very quickly, I'll do it in a different colour. Do it in red. Okay, normally, normally you're used to questions like this. You've got 2 supports. You might have a number of forces. You project your lines down. Oops. Then you end up basically going up a bit, down a bit, down a bit further, down a bit further, and then you go up again, and it should equal 0. So you have, use another different colour actually. You'll have something like that. That's the shear force diagram, isn't it? Right, it looks something like that. And what we end up doing is, oops, that'd look like that, I suppose, wouldn't it? Okay. We end up working out the area of those, because that's force times distance. Okay, and then we plot the beam bending diagram, which will end up looking something like that. Okay, we've essentially just skipped a stage here, and instead of working out areas and doing it the long-winded way, which is great if you're asked to do a shear force diagram as well, we're just going to use the basic principle that a moment is force times distance. Okay, if this was a beam, let's see if I can rub some of this stuff out here. If this was a beam with just one force, okay, the maximum bending moment would simply be force times distance, and it'd be dead easy. So it'd be 2,000 times 2 if there was just that 2,000. If there's just a 3,000, it'd be 3,000 times 4, 12,000. However, they sort of compound. So you've got to work from the pivot when a cantilever and go along. So I'll do it again. So at point 0, the force, well, there is no force, it happens. Even if that was a million kilonewtons, the moment's still 0 because it's 0 distance from the pivot. Okay, so 0. 2,000 times 2 takes us to 4,000. Still don't know how to do that. 4,000. 3,000 times 4, 12,000. But we're already at 4,000, so it takes us down to a further 16,000. And then our last point of significance, there's no force, so it's 0 times 5, which is 0, so it brings us back up to 0. So that's our bending moment diagram, and it so happens that our maximum bending moment is 16,000. So there we have it. That's how I got that M for 16,000. Right, I hope that is of some use. That was a bit of a cruel last question, but the first two, absolute piece of cake, especially if you practice them and you'll be ready for them if they come up. On to question 2, that'll be the next video.